try and give you a very quick introduction to, I think, some of the most interesting parts of it. I'm then going to move on and talk a little bit more about astronomy, but in the context of applications of astronomy and actually what impact can it have on your everyday life, because it's all well and good gazing up into the stars, but really does it do anything for us? And hopefully I'll be able to convince you that it does. And then maybe that will inspire you and think, oh, this has been really interesting, or I can really see the applications of this. I'd quite fancy getting into it as a career. So I'll give you a little bit of an overview as to what a career in astronomy and astrophysics looks like. So yeah, let's see how I go for time. I will whistle stop tour. Let's go. Oh yes, and if you do have a question, pop them in the chat box. Actually, the way I'm set up, I'm not necessarily going to see that question straight away, but yes, at the end of the talk, there will definitely be some time for questions. Just to give you a little bit of context about me, so that I'm not just a disembodied voice coming through the internet. I've been an astronomer for nearly 10 years now, and I got into it initially as a hobby. Just your kind of stereotypical backyard astronomy, go out in the dark in a field somewhere and look up at the sky with a telescope. I then went off to university to take it a little bit more seriously. So I did my MPhil, so that's an integrated master's in physics with astrophysics at the University of Manchester, and really enjoyed that. So I've stayed here in Manchester, and this year I am just finishing off my PhD in astronomy and astrophysics, again at the University of Manchester. So I have a background in practical astronomy, so the kind that people can do, there's no special training required, but I've also been studying the science behind it over the past few years as well, and I do like bringing those together and linking what you can see to the science behind it. I think one thing to get clear, actually going into the talk, is some definitions. Now, these aren't official dictionary definitions, they're just ones that I think I would define these different words as. And it's very easy to get them confused. So for me, astronomy is anything that involves observing the things beyond the Earth's atmosphere. So anything in space, if you're observing it, if you're studying it, if you're writing down some maths that describes it, anything you like, I would say anything relating to space, to me, that is astronomy. Whereas astrophysics, a little bit more specific, I would say that's more the scientific study of celestial objects. So there you're wanting to apply mathematical theories to what we can see. It's not just about making pretty pictures and enjoying the nice view, it's also using that to understand the universe that we live in. Cosmology is well, you could say it's a sub-branch of astrophysics. You could say it's a separate area of physics entirely, but that relates to studying the universe as a whole. So kind of thinking about the really, really big picture. And those three are all not to be confused with astrology. It has been done many a time, and I do not blame you at all in the slightest if you have used astronomy and astrology interchangeably. Historically, they were very much the same thing, and astronomers studied the stars, studied the heavens, because they thought that it would have some kind of influence on their everyday lives. Now, we now know that this is not the case. It's not scientific at all, astrology. Horoscopes, they're just a bit of fun, really. There's nothing scientific to them whatsoever. So I'm not going to be talking about any of that, but just to clear the air before we get going. So hopefully I have done that. When I'm talking about astronomy, I could be talking about maybe three separate things. And there's this distinction, I guess, to be made between the astronomy that you do just by eye, if you just step out of your house on an evening, look up and see some stars, you're doing astronomy. You can take that a little bit further, you maybe use binoculars, use a telescope, start to really hone in on particular parts of the night sky. And then that is maybe a bit more serious astronomy or amateur astronomy using telescopes. And then you've got all the way up on the very serious scale, you've got your professional astronomy and astrophysics. So these are your very expensive, high-tech scientific instruments that are there to monitor, study, image, do anything. So here are 3 different images of Jupiter. So the first 2 I took, the third one, sadly, I did not, of what Jupiter looks in the sky just to the naked eye, what it looks like through a fairly standard amateur telescope, and then what it looks like kind of in these flashy images that we see from the Hubble Space Telescope or missions that go out to the planets. So it's very easy to get disappointed, I think, sometimes when doing astronomy for yourself, because you might expect to see the things that we're very lucky now to get close-up images of. That's not the case, but I think there is still something there in seeing it with your own eye, and that light that has come from the planet or star or whatever you're looking at, and I think there's more of a personal connection there. So it's still worthwhile doing, definitely. Now, the thing with astronomy is that I would say one of the main things that makes it stand out against other areas of science and what makes it different is that we can't interact with it as we would say if we were doing an experiment in the lab. Particle physics, they've got the Large Hadron Collider, they can smash particles together to their heart's content and see what comes out of it, and they can design studies and test their ideas and see if the science holds up. We can't do that in astronomy. For pretty much all of astronomy research, the only thing that we can do is look, observe what's out there. And in general, the connection that we have with the universe is the light that we get from it. And light is a wave, an electromagnetic wave. So you can think of it as, these little waves of light going backwards and forwards, or wherever the light is traveling. And here is an image that you might be familiar with. Maybe even if you're just a music fan, you might be familiar with it. But what it's showing is that white light, so just light that we would usually have around us, is made up of all the different colors of light. So when you split that white light up, you get all the different colors of the rainbow. So we see this in rainbows as well. And what you can hopefully see from this diagram is that the only difference between the red waves and the purple waves is that they're a different wavelength. So what that means is that the red waves are slightly longer than the blue waves down at the bottom, and that affects how they behave. So in this prism, the red light is coming out on the top and the blue light is coming down on the bottom. And so when we think of light, don't necessarily automatically think of the colours of the rainbow, but really what light is you can have light at any different one of these wavelengths, and astronomy doesn't limit itself to just the colours of the rainbow that we see here. And actually, there's a whole world beyond this optical range. So we've got going past red, we get into infrared, very aptly named, and it might be something that you've come across before if you have looked at a thermal imaging camera or a night vision camera. They use infrared light in order to see things, and we can't see it with our own eyes. It's just a little bit off the side of the red end of the rainbow. And you go even further and then you hit the radio. Now, I'm personally a radio astronomer, so I'm particularly a fan of this part of the electromagnetic spectrum, the spectrum of light that we have. That's going off one end. When we go the other end, we get to ultraviolet, X-rays and gamma rays. Now, one thing that this diagram is showing is that not all of these different kinds of light get down to the ground, which is a good thing. We do, especially that high energy end over on the right, where we've got ultraviolet, X-rays and gamma rays, we don't particularly want to interact with those as much as you would necessarily in space, especially ultraviolet. If you've ever had a sunburn, you know how nasty it is. So really it's quite fortunate that we do have that layer of protection in the ozone layer to stop it. Unfortunately, that also means that if we are wanting to observe ultraviolet or X-rays or gamma rays from space, we have to go above the atmosphere to do that. So that's why a lot of telescopes are up in space. So either the wavelengths that they're looking at are blocked by the Earth atmosphere and the ozone layer, or other things as well. And even for the two parts of this spectrum that make it to the ground, so that's radio and optical, even then for optical, actually you can get the best views when you kind of go away from the atmosphere and you're not getting that kind of interference anymore, I guess. So because we've got all of these different kinds of light, there are all sorts of different ways to collect it, and telescopes do come in all shapes and sizes. The image in the middle here might be one that you're most familiar with, and that's your standard back garden telescope that uses optical light. You can scale that up a little bit, and on the right, there's an image there of the VLT, which is the Very Large Telescope. So it's essentially the telescope in the middle, just bigger and with mirrors. That's very overly simplistic, but it works on a very similar principle of collecting up the light and magnifying it so that we can see things that are a lot fainter than what our eyes can see. The rest of the images on the screen might not look as much like telescopes. On the left, we've got the Hubble Space Telescope, which is actually just what you again might call a normal telescope, just up in space. And then the one on the bottom is XMM Newton, which is an X-ray telescope, and X-ray telescopes collect light in a little bit of a different way. Possibly the strangest looking are radio telescopes. In the top right, we've got the Lovell telescope at Jodrell Bank Observatory, so definitely one that has that I have a soft spot for. And those collect radio waves. You can either use a dish, or you can even use dipole antennas. So just your standard strip of wire, use them to collect a low frequency radio signal. So that image in the middle at the top is part of the LOFAR telescope, which collects really, really long wavelength, low frequency radio waves, and uses them to look at space. So there really is a huge range of different ways of looking into space. And each of these different wavelengths can tell us different things about what we're looking at. So hopefully that has given you a very quick introduction as to how we do astronomy. I realise I'm going through this very, very quickly. Let me just see actually if I can have a look at the chat. I don't think I can do that because chat, just so that I can...
Yes. There is a question here. Is ultraviolet more red than blue light since its wavelength is shorter?
So if I just go back to this diagram here, so ultraviolet is off this end here, so it's got a shorter wavelength. So when you go down here, you're getting just a shorter wavelength. So ultraviolet is beyond violet, so it's going that way. So it's the shorter wavelength, and then so red, that's the biggest wavelengths, and then right going up there. Hopefully that clarifies things before I move on.
There's another question if you want to take this here. Any advice on how I can take pictures using my telescope?
Yes, I can do. I will talk about this very, very quickly. So actually my favorite method, and the one that I use to take this photo here, is just to borrow someone else's telescope, because chances are you probably don't have a telescope of your own, and then you can just hold your phone up to the eyepiece, and just the way that you would look in, you can take a picture just using your phone camera. To be honest, that's the way that I started doing photos, and I do find it the easiest way to do it. So how to take pictures using, and if you've got your own telescope, that's even better. I would say the easiest way to do it is to hold your phone up and kind of get used to it that way. There are other ways of doing it. You can get specialist adapters where you can put webcams into telescopes and to take pictures like that. To be honest, that is a whole other lecture talk that I could give on that. So I might have to leave it at that, but I would say all the guides to that are online. So that's the way that you can take pictures yourself. And if everyone is then happy, I realise again I'm moving on quite quickly. I'll hopefully have some time for some more general questions at the end. Let's go back to basics, because I've kind of, I feel, thrown you in at the deep end a little bit here, and it's sometimes not even intuitive as to some things that people might consider, oh, that's basic astronomy. Other people, you might not have come across it before, and that's okay. So just to clarify a few things, where are we? Well, we're on the Earth, and the moon orbits around the Earth. So that's why we can see the moon at different parts of the sky at different times. It's because it's moving around us, and its orbit takes about a month. And then it's the Earth's orbit around the sun that takes a year. So we've got the moon orbiting the Earth, and the Earth is orbiting the sun. Now, the sun is actually quite important when it comes to astronomy and our life on the Earth. Obviously, it's our source of energy, it's our source of warmth, it's what allows for life on this planet. However, it is also very powerful, and we are protected from this power by the Earth's magnetic field. We've got something that's called the solar wind. So these are energetic charged particles coming towards the Earth. They're always streaming by. It's nothing dangerous, but the Earth's magnetic field helps deflect those away, just so that we don't get too much of a big hit from the sun. And we see this interacting with the Earth's atmosphere at the poles. So the northern lights and the southern lights, they occur because the poles of the Earth are where the magnetic field lines come out of, as you can hopefully see on this diagram. And so these particles, the solar wind from the sun, that's where they can access the Earth's atmosphere, and they get in, and that interaction causes the northern lights. So we see that on a regular basis on the Earth, and we're seeing that energy from the sun. And it's quite important to understand this, not just for understanding when we might get a pretty picture in the Arctic, but solar flares can disrupt electronics on Earth. There have been historical events where there's been maybe a less level of technology than we have today. So if they've had telegrams or something like that, and a solar flare has kind of disrupted that and disrupted those communications. So it's something that's important to understand and track, and recognize if the sun gets more energetic, if that is going to affect us on the Earth. So that's why solar astronomy and solar astrophysics can be very, very important. So I've talked about the sun and the Earth and the moon, and I'm going to let that run for a little bit, and I forgot about the music, if you can hear the music, and then I'm going to stop it. So what we've got here is, what you can see from the video, hopefully, is that how our solar system is set up. So we've got the sun in the centre, and it's orbited by all of the planets in our solar system. So the four little ones closest to the sun, that's Mercury, Venus, Earth, and Mars. And they're what we call the rocky planets, so ones with a surface that you can stand on. You head out to the gas giants, so you've got Jupiter and Saturn, and then Uranus and Neptune. And they consist of the 8 planets of the solar system. Now, in this diagram, we've also got Pluto. Now, Pluto is a little bit of a contentious issue in astronomy, because lots of people remember it being a planet, and a lot of people don't understand. are angry. Why is Pluto not a planet anymore? Well, it is kind of, it's a dwarf planet, and I'll talk a little bit more later as to why Pluto, actually, the more we understood about it, the more we realized actually that it's not a planet. It's still important, it's just not what we would consider to be a planet by the current scientific definition of it. And one of the reasons is you can see that it's a bit of an oddball compared to the other to the planets that are shown on here, because whilst all the other planets kind of orbit quite nicely in a disk, Pluto just goes up and down. It's not really wanting to stick to that same plane as the other planets. So there it's going off again. A little bit more music. Actually, while you watch that, I can check the chat again as well. So we've had a good question, a couple of good questions that I'll answer now. So first of all, the question, why does the moon orbit around the Earth and not directly around the sun? So this all comes into how the planets and the moon and the sun, how they formed. So initially, the sun came into existence and it was formed from lots and lots of kind of material all coming together, and I'll talk a little bit more about how stars are born and the life of stars in a little bit. And so then there's all this material then still coming around the sun, and it's kind of that disk of material kind of orbiting around the sun that came together to form the planets. Now within these planets themselves, there'll have been lots and lots of material kind of around, and in the early solar system, we think that it was quite different to the setup that we see today. And one theory as to why the moon exists is that the Earth had just formed relatively recently, but then it was involved in a collision with another planet, probably about the size of Mars. And so what happened was these two planets came together, swirled around each other, came together, and then a little bit of debris came off, and that bit of debris from this collision coming together formed the moon, and that's why we think the moon exists and where the moon comes from. And so that was kind of already part of the Earth-Moon system, and then that was all already going around the sun. And I'll talk a little bit more about moons in a bit as well, but in general, moons go around planets, planets go around the sun. We have another good question about the solar wind. Is it just the term, or is there actual wind being released? I believe there is no atmosphere. Yeah, so the sun is a very, very extreme environment. It's made up of what we would call plasma. So think of gas, but very, very hot. So much so that the electrons and the protons and neutrons, the things that make up atoms, the electrons, essentially they're ripped off their atoms. They kind of don't exist within atoms. It's all just kind of one loose soup of particles. So yeah, it's very different. It's not anything that you can necessarily think of as being atmosphere or air. And when it's talking about a wind, what the name refers to is the fact that as the sun is kind of it's streaming out these charged particles as it kind of is undergoing the processes that give out light again, which I'll talk a little bit about in a bit. So no wind being released. It's not air as you know it, but it's called a wind because we can see it coming out from the sun, and it does have an effect as it comes outwards. And we've got a few more questions, but I think they're ones to leave until the end because they're some interesting questions, but not related to what I've said so far. So let's move on. Planets. Where does the word planet come from? Well, it means wanderer. So the Greeks, when they were doing their astronomy, they noticed that planets moved in the sky relative to the stars. So because they're also going around the sun, they appear to move in the sky. And you saw in the animation before that they all go round kind of along the same, what we call a plane. So they're going around like a disc, almost like a turntable. And so that means that they follow roughly the same path as the sun in the sky. So when we're observing all of these things from Earth, we're looking at that from a particular angle, and we'll see that the planets follow roughly the same path in the sun, in the sky as the sun. So they'll rise in the east and they'll set over in the west. So that's one way that you can identify if something's a planet in the sky. Another thing is planets often appear brighter than stars, and they don't twinkle. So stars twinkle because of distortions in the atmosphere, in the air. So as the light is coming into our atmosphere, it can, depending on what the air is doing, if you've ever looked above a surface on a hot day, and the surface is very hot, and you can see the air dancing potentially. It's that same kind of effect that causes a star to twinkle. Planets don't have that effect as much, because rather than it just being a single pinpoint of light from far away, it's more of a disk, a very small disk, and we can't really see the full circle of it. But that helps stop it from dancing around so much and twinkling like a star was. So if you're looking for a planet, what you're looking for is something that's probably brighter in the sky. In fact, this photo that I took back in 2013, it was a conjunction of Jupiter, Mercury, and Venus. So they move about in the sky, they move relative to each other. Sometimes they'll appear closer to each other, sometimes they'll appear further away. And so this was taken at sunset, so before it had got properly dark, and you can clearly see those 3 points of light, and they refer to those 3 different planets. So definitely, I would say planets are some of the first things to start looking out for if you're getting into astronomy. Something that you might have seen in the news recently, or it might have come up on social media, you might not have heard of it. It depends, it's fine either way. Mars is currently at what is called opposition. Now, these kind of astronomy terms get bandied about a lot, and think, oh, something's at opposition, or there's a conjunction, or something like that. Often refers back to astrology, as I mentioned before, which I'm not going to go into because it's not astronomy. But all opposition means is that it's opposite the sun in the sky. So in that little diagram that I've got on the bottom left of my screen, we've got the sun, we've got the Earth going around the sun in an orbit, and we've got Mars going around the sun as well. And because the Earth is closer into the sun, it travels around faster. So in this diagram here, Earth is undertaking Mars, so it's going faster than Mars, and it's going past it. And so as the Earth is overtaking Mars, as it comes between the sun and Mars, that means that Mars is opposite the sun in the sky, and it's also the closest to us that it gets. So it appears bigger in the sky through a telescope. So I've taken this series of images here, which was featured on APOD, Astronomy Picture of the Day recently, showing how Mars has looked over the past few months. And it goes from looking like a very, very boring red blob. To be honest, that's my opinion of observing Mars a lot of the time, but it can get nice. And we can see, if you were looking at it through the same telescope on these different nights, it would look bigger in September or at the moment than it would do previously. And that's because the Earth undertaking it on its orbit, getting closer, and so it appears bigger in the sky because it's closer to us. Now, this effect you can only really see with a telescope, but it's something that you can notice with your eyes as well. In fact, Mars is looking beautiful at the moment. If you see a very bright red light in the sky and it's not moving, it's probably Mars. It is looking very, very nice at the moment. So that's what it means by opposition. So if you ever see something like, oh, Jupiter is at opposition, Mars is at opposition, all it means is that it's opposite the sun in the sky, and that's the best time to view it. So Mars, one to watch out for at the moment. In general, observing the solar system is a great place to start when it comes to astronomy. So you can pick out the moon and the planets with your eyes. Planets are a little bit trickier, and they do tend to have you do need to have a little bit of practice spotting them sometimes to know for certain if they are or not. Mercury and Venus will only ever appear at sunrise or sunset. Mercury is quite hard to spot, so I would say that that's an observing challenge for once you've maybe gotten into astronomy a little bit. Venus is very, very bright. You cannot miss Venus when it is in the sky. You can see a little bit more detail of planets in binoculars. So for example, lunar craters or moons of Jupiter, or even if you've got a camera with a good optical zoom and a tripod to hold it steady, you can take some really great photos. For the best views, you use a telescope, but I think that goes without saying when it comes to astronomy. The only exception to that is during a meteor shower, you actually don't want to use a telescope because you're magnifying a small patch of the sky, but then you're only looking at that small patch of the sky. And for meteors, you want to be observing it all. And just to give you an example, these are some photos that I took of the moon. And they are taken on consecutive nights. So from the first night that the crescent was visible in the lunar cycle, all the way up to what we'd call the first quarter moon. Again, lunar cycles, lunar phases, that's a whole other talk, and I'm really trying to, I realise I am not going through this as quickly as I had practiced, but it's fine. You've had some really good questions coming in, so I will just see what I can get through. Oh, another nice thing that you can observe in a telescope are the moons of Jupiter. Now, Jupiter has got many, many moons. To be honest, I lose track of the number of moons Jupiter has because we're still discovering more of them. That's still ongoing science. We're finding more moons of Jupiter. But the 4 biggest moons of Jupiter are called the Galilean moons. And over the course of an evening, so this is a series of images taken over the course of a few hours, you can see those moons, and those moons are orbiting Jupiter. So as I said, moons orbit planets, planets orbit the sun, and here we are, 4 of Jupiter's moons. And actually these moons are big. Ganymede, which is the 3rd moon, so the second from the left, is bigger than the planet Mercury. So these are not small. And you know, so actually some moons can be as interesting, if not more interesting, than planets. So we've got Enceladus, which you can see that lovely surface on there. So that's ice on the surface of Enceladus. And there's talks of, do we send a mission to Enceladus to try and see what's under the surface there? We've got Titan, again, very, very large, bigger than the planet Mercury, has got really interesting things going on in its atmosphere. And we've got Io, another moon of Jupiter. Some really interesting volcanic activity happens on Io. So I'm not going to go into this too much because I'm not a planetary astronomer or a planetary scientist. But if you are interested, really there is so much to discover just within our solar system. Let me have a look at the chat again. Just see if there are any more questions about what I've said so far, because I think it's probably better to clarify before I move on. So yeah, Mars is at opposition. Well, it was at opposition the other day. I can't remember exactly when, but yeah, it's still a very good time to see Mars. What happens if a star collides with a planet? Really, that planet is just toast, I'm afraid. Stars are so much bigger than, so much more large than planets. To be honest, the planet would just get swallowed up by the star. It's not very often that a planet would collide with a star. For that, there would have to be some kind of big cataclysmic event, because usually orbits can be very, very stable, and it would actually take quite a lot to knock something out of orbit and to hit a star. But yeah, it wouldn't end very well for the planet. Oh, another great question. Are the moons of other planets formed the same way as the moon for Earth was formed? maybe these are actually questions that there is still active research going on. As I said, this is not my field. I can't say that I'm an expert in it, but yeah, we're still actually trying to study and work out the origins of our solar system and how different objects were formed. And so it could be that they are the result of collisions. It could be that they were formed in different places and then they were captured by gravity. So there are lots of different ways that a planet can get its moons. And I won't go into them, but it could be one of the things. Could Earth become a moon of Jupiter if it were to pass by it? I mean, it's maybe a little bit light. So it would, for the Earth to pass by Jupiter, it would need a lot of energy to move the Earth to close to Jupiter. So when we think about firing rockets and space probes to go and visit things in the solar system, the amount of energy that requires is very, very large. And that's just for one tiny rocket. To move the Earth, that would, I don't even want to think about the numbers involved in that in terms of the energy. If an Earth-sized planet were to happen to wander into our solar system, maybe it's been ejected from its own solar system, because there are some planets which we do see floating about, free-floating planets we call them, that don't have a star attached to them. It could be if one of them happened to drift into the solar system. This isn't going to happen, by the way. These are all very much hypotheticals. I'm not saying we're getting a planet into the solar system anytime soon, but it's possible that Jupiter could capture it with its gravity. But these are things that you kind of need lots of maths to try and simulate what would happen with the gravity. And yeah, I'm going to leave the questions for now, because otherwise I feel like I am not going to get anywhere with this talk. These are all great questions, by the way. I quite like actually this, because usually with a talk you'll just stand and you'll give a talk, and I quite like the back and forth with this, so I'll keep going like that, I think. Just to comment about dwarf planets, because I mentioned Pluto before. Actually, Pluto is smaller than our moon, so the moon is to scale here. So we do have a few other dwarf planets in our solar system. It's not just Pluto, so don't worry, it's not been demoted and is now just sat on its own, lonely in a group. And actually, I realised this graphic from space.com must have been from before we visited Pluto, because it's not had the lovely updated New Horizons image of it. Yeah, so in our solar system, we've got these dwarf planets. We've also got asteroids and comets, so we've not just got the planets. In particular, there are a lot of asteroids between Mars and Jupiter. It's called the asteroid belt. Although I will say, if you're into your sci-fi films or TV programs, and you've ever got a space shuttle going through an asteroid field, and there's asteroids and they're having to dodge, weave in and out, that's unfortunate. Well, luckily, maybe unfortunately, if you like the drama of it, but actually the asteroids are actually spaced very far apart. So even if you are passing through the asteroid belt, you might not even see an asteroid. Comets are a little bit different to asteroids. They tend to have really, really what we call eccentric or elliptical orbits around the sun. So that means that they come from very far out away from the sun, and they come in very close to the sun and swing around and come back out again. So if any of you managed to see comet Neowise that appeared in the skies earlier this year, really it was the first time I'd seen a comet. I was very, very excited by it. And so what happens there is, as a comet warms up, as it comes in closer to the sun, the ice that forms part of it melts and kind of immediately kind of vaporizes, and that forms part of this lovely tail that you can see coming off comets and kind of giving off dust as well. So asteroids and comets, both small, kind of mostly rocky objects that are in our solar system. They're not round typically, so although the planets are round, that's because they're a lot bigger and they can pull themselves together into a round shape. It's not the case for asteroids and comets. They tend to be a lot lumpier. But that's a very quick introduction to what they are. And another thing that we have in our solar system, meteoroids. So these are just very, very small bits of rock or metal or a mix of both, much, much smaller than an asteroid. So we call them meteoroids when they're in space. When they enter the Earth's atmosphere, that's a meteor, and a meteorite is what's left if it hits the ground. So different, very similar terms that mean slightly different things. And kind of going beyond our solar system, because we've not even, I've been talking for nearly 45 minutes and I've not even scratched the surface of this yet, but going beyond our solar system, actually we launched over 40 years ago, so the Voyager probes, and we've launched a few probes out over the years, and it's currently 14 billion miles away. So its signals traveling at light speed take 21 hours to return to Earth. So I think there was a question in the chat earlier about that, actually. So very good question there. Yeah, when something goes that far out, even traveling at the speed of light, its radio signals 21 hours about that to return to the Earth. And those signals are very, very faint. So radio signals tend to spread out and kind of dissipate the further they go, and so now it's only the very biggest dishes on Earth that kind of can pick up those signals. We've got something called the Deep Space Network, which is a network of radio telescopes, satellite dishes around the Earth that can keep track of these probes that are going away from us, and they're going away very fast. It's traveling at 7 kilometers every second, so it would take about a minute to go from Land's End to John O'Groats, the whole length of the UK, in about a minute. So that's quite speedy. But even at this speed, if it was traveling in the right direction, it would still take 75,000 years to reach the nearest star. So yes, space is big is the conclusion there. And I'm going to skip over this, but there's so many different ways that you can define the edge of the solar system. So yeah, there's not a hard edge to it. So if you see anything like Voyager has left the solar system, there's not really a defined edge. There are lots of different ways that you can define it. I'm going to give you now the whistliest of whistle-stop tours of the rest of the universe, because I do want to touch on the other things that I mentioned, and I'm conscious that I don't want to keep you here for too long. But stars, let's go for a quick lesson on stars. Red stars are cooler, blue stars are hotter. Now, this might seem a little bit counterintuitive because you think red is hot, blue is cold. Opposite way around. If you think of a flame burning, the hottest, if you think of a very, very hot flame, like a Bunsen burner type flame, those are blue. And that's because of the physics behind it means that blue means higher energy, more heat. And in general, redder, cooler stars live longer than hotter, bluer stars because their fuel lasts longer. They're not burning through it as quickly. And I say burn, sorry, it's powered by nuclear fusion. So these are, so what stars do is they bring atoms together to create new atoms, and that releases the energy that is given out as the radiation from stars, the light. Often you find stars in clusters. Here are some pretty pictures. I'm going to skip over them, I'm very sorry. But these are some things that are very, very lovely to have a look at in a telescope. And I mean, I'll flash this up. I don't think I need to talk you through it, but stars they go through a lifetime. They are born and they are formed. They live out their lives. The sun is about halfway through its lifespan. It's been around for about 5 billion years. It's got probably about another 5 billion years left of fusion. And depending on how heavy a star is, so how much mass it has, it can end its life in various different ways. It can end up as a supernova, and that could go, for example, into being a neutron star or a black hole. So actually a lot of different things that you might have heard of in astrophysics, they could just be some part of stars and the stellar lifetime. Again, a whole other talk in itself. I realized I was being very ambitious trying to fit in everything about the universe in this time. And I just wanted to mention, because we had a few questions about planets earlier, is that so exoplanets are planets around other stars. It's not just our solar system that has planets. In fact, we think that the majority of stars that we see, they have planets themselves. And we can see here in the Orion Nebula, so if you can see the constellation of Orion in the sky, the 3 stars that form his belt, and then his sword hanging down from that, in his sword is the Orion Nebula. And there where we can see these are images of newly formed stars, and there's leftover material from those stars come together to form planets. And actually studying these other stars and their planets is what helps us understand where our own solar system has come from. I'm going to pause here for a second just to see if there's any quick things to answer. What's the wavelength of the light coming from the sun? Lots of different wavelengths of light. It's a lot of it is in the optical, so the light that we can see, but we do get other wavelengths as well. Actually, a lot of them might be blocked by the atmosphere as well, which is another thing. And I'm going to leave those there. And what I'm going to do is I'm going to skip on just a little bit. I want to talk about this slide because it's something that's been in the news recently. And one thing that I wanted to highlight is that when you think about astronomy, and when astronomy is reported in the media a lot, it can be very sensationalized. So recently there was a scientific report released about phosphine on Venus, and I realize I have spelt it wrong. That serves me right for putting this slide in at the last minute. But what happened recently was there was a detection of this molecule called phosphine. And actually looking back, it may have been detected on Venus before. So we know, okay, it's pretty likely phosphine is on Venus. So that's something that we were fairly certain on. Now, there's speculation as to why there is phosphine, this particular molecule on Venus. And in essence, in the science that we know, it can either only be produced in factories or biologically. And so this was why there were a lot of headlines recently about, has life been found on Venus? Well, no. There's some evidence of a molecule that could have been produced biologically, but actually the likelihood is it's probably just some new chemistry that we've not encountered yet. Venus is a very, very extreme environment. Think of global warming and the greenhouse effect. Venus has the greenhouse effect in runaway. It's very, very hot. In fact, it's even hotter than Mercury. Even though Mercury is closer to the sun, Venus is hotter because of this greenhouse effect. What I'm going to do is, I was going to go a little bit more in the rest of the talk about, everything that we see is within the Milky Way galaxy. And kind of when we go out beyond that, there's all sorts of other weird and wonderful things, but they're things that actually you're not necessarily going to be able to see if you're doing astronomy yourself. So actually, it's probably something that we can leave. Just so I am going to go over a little bit over time, but I have been answering questions as I go along, so I'm going to say that I'm allowed to do that. I just want to highlight a little bit about what astronomy does for us. So hopefully I've given you just a tiny little taste of what astronomy is and the science of what is going on in astronomy. But what is the point of it? It's all well and good knowing these things, and some people are happy that we're learning stuff for knowledge's sake, and other people just think, well, it's a waste of money. In fact, this was something that I saw on a Facebook thread earlier, and kind of someone had commented about the Venus discovery. Oh, it's a waste of money. Why are we looking into this? Well, first of all, we don't shoot money into space. I think there's some kind of misconception that money spent on space exploration, we just fire money up in rockets. That's not what we do. Money spent on astronomy, money spent on those missions is money spent on employing scientists. So it's just the same as any other job, really. You know, we have our jobs, we do some science, and then we do other things with our lives, go out and spend money, help the economy, all that kind of stuff. So it's just scientists are people too, and we function in society, and we need to get paid. We also can use astronomy to develop our skills, and actually astronomy comes across some really big technical challenges, and by applying scientists to solve those challenges, we can also go then elsewhere, and help solve other challenges that maybe do have slightly more real world applications. So yeah, development of technology. To be honest, I think that the other one, the ones at the bottom, are enough. Answering fundamental questions and inspiring future generations. I think that's enough as to why we should be interested in astronomy. But if you think that's not enough, then there are other reasons too. In fact, another topical reason as to why astronomy is useful. So astronomers, we're used to handling what's called big data. So telescopes produce a lot of data, so especially radio telescopes. As I mentioned, I'm a radio astronomer. I work on radio telescopes. And at any one time, I'm probably working on just under 3 terabytes of data. I've got my hard drive sat on my desk next to me. It's got a load of data on it. Just for comparison, a typical Excel spreadsheet has less than 1/100th of that. So yeah, I could deal with, you know, hundreds of Excel spreadsheets worth of data, and you know, that's something that I do on a daily basis for my job. And so one of the skills you have to know as an astronomer is proper data handling, and as we've seen in recent news, that can be very, very important. So actually a lot of astronomers will go out into other industries and apply the skills that they have learnt in other areas, which, yes, quite important. Transporting that data as well. If you've ever complained about how slow your internet connection is, I have to get my data from Australia, and it's getting better, but yes, it still takes a very long time. So that's something that astronomy is working on as well. Wi-Fi, invented by a radio astronomer. Again, this is a whole other talk that I could be giving right now about things that have originated from astronomy, and actually the technologies that have been developed for astronomy, we can apply to other things. So as I mentioned, Wi-Fi, that originally came from Australian radio astronomers, and I would imagine that the majority of you, if not all of you watching this talk right now, are using Wi-Fi. So you've got radio astronomers to thank for that. And in fact, just any communications really. Here's a photo of a satellite TV dish and TV aerial. They look very similar to telescopes. So on the left there is a radio telescope in the Netherlands, and on the right is an artist's impression of kind of an up-and-coming radio telescope called the SKA. And yeah, it's the same technology. So things that are developed for radio telescopes can really help with communications as well. And again, this is a diagram showing the strength of Wi-Fi in your house, and kind of you can apply the same physics as you use in astronomy to everyday problems like, why is my Wi-Fi connection bad in my bedroom? If you move the router around a bit, you might find a sweet spot where you can get more of a connection in the house. Medical imaging. I've barely even talked about black holes, which again was what the Nobel. I did write this talk actually before the Nobel Prize was announced. Yeah, techniques for observing things like, for example, black holes. So this image of the black hole by the Event Horizon Telescope used a technique called aperture synthesis, which was developed for astronomy and helped develop medical scanning. In fact, I did a module in medical imaging during my physics degree, and I was amazed by how similar the science was to astronomy. So there are so many transferable skills there. Again, there's a whole other talk you could do on this. People are using astronomical image analysis techniques to help conservationists. So again, another real world application of things that were developed for astronomy and now are being used elsewhere. So I'm just going to leave this up here. So many other things. And just to, if hopefully I have not run through this so quickly that you're sat there like, oh no, what's gone on? If you are thinking, oh, actually, maybe I do want to look a little bit more into astronomy, be it for a career or for just as a hobby. Generally a conventional path. This is the path I took. You might do A-levels, including physics and maths. You might do an undergraduate degree in physics and then do a postgraduate degree specialised in astrophysics. So that's the route that I'm taking. Many people do it differently. And in fact, there are so many ways into astronomy research. So you don't have to have a background in physics and maths. It could be that you're doing another science, chemistry, biology. So for example, the recent Venus discovery that was announced, they consulted with chemists and biologists. Engineering, computer science, these are all things that are used and are needed in astronomy research. And equally, if you do get into astronomy research, you're then not limited to astronomy then for the rest of your career. And, a lot of people might go into being researchers, lecturers, professors, but to be honest, most people who are in astronomy research won't go down that route. A lot of them will then go into industry research, software, data analysis, so much more. And any path is valid to take. Don't think, oh, this has been really interesting, I want to do this, but it's too late. It's never too late. And always, you can have astronomy as a hobby as well. I'm doing this from, I guess, maybe a careers and a very science-focused perspective. But one thing I think to never lose sight of is that astronomy is just, it's really awe-inspiring and it connects you to the universe. You don't have to have anything. You can just go out and look. You can connect with people who have the same interests as you and just start learning and start sharing more. And this was something, again, I'm not going to be able to give this the time that I wanted to give it to, but I've been putting this in my talks recently, and I just want to say astronomy is stronger when it comes from a community grounded in respect and diversity, and astronomy is not immune from a lot of the societal issues that we have been talking about at the moment. And so there's a couple of articles linked here which kind of go into that in a bit more detail. And right, I've skipped over a lot. I've gone over my time, but I was answering some questions. And if you are interested anymore, I am over on Twitter. I do tweet mostly about astronomy. Sometimes it's cats. Hopefully you don't hate cats. I also sometimes will speak on something called the Jodcast, which is the podcast we do from the Jodrell Bank Observatory. I am going to stop sharing here, and thank you all very much for listening into my whistle stop tour. And I am hopefully going to go for some questions if we have time. I realise I have pushed it to the limit. I'm sorry.
Yes, I think maybe if you could see the chat box, there's quite a lot of questions there, man. If you want to pick.
So
some of them.
Yeah, so I have had a question about how maths heavy is astronomy. So if you're wanting to do it kind of astrophysics and be a scientist doing astronomy, you do have to have a reasonably, you need to be happy with maths. I wouldn't say you need to be a whiz at maths. There's not necessarily a thing of being naturally gifted at it. It's just, as with anything, it's something that you can work at. A lot of astronomy is done via programming and coding, and that kind of is along the same vein as maths, where you kind of need to have those logical thinking skills in order to do it. So it depends really. If you're going into theoretical cosmology, that's pretty much all maths. In fact, I'm scared of it. There's too much maths there for me. If you just want to go out with a telescope and do some stargazing, very minimal maths. So really, it's up to you. Let's have a look. Do you recommend studying astronomy for an aerospace engineer? So if you're already within aerospace engineering, I would say it could be something that supplements what you're learning. I think, as with anything, what I'm not trying to do here is say you need to know astronomy and you need to study it. I would say that if you're interested in it and it's something that, you know, you have the opportunity to pursue, so with, for example, being an aerospace engineer, if you're interested, you could potentially find a career path which takes you into designing spaceships, you know, craft that we send out, be it with scientific instruments or maybe going into the future, even human missions. So yeah, I mean, if again, I would recommend it, but I'm biased. I think astronomy is great. So yes, let's have a look.
There's about 35 questions in total, I think.
Yeah, I was going to say, to be honest, I feel like I could spend a whole hour just doing a Q&A.
Maybe you could pick one or two from there. Maybe if you want to pick one or two from there, and then.
Oh, so the question, what signal was the WOW signal? So for context, the WOW signal is a signal that was picked up by radio telescope. I can't remember the year. So there's a whole branch of astronomy called transient astronomy, and that's all about things like that flash that go off in the sky but aren't there for a long time. So things like stars, things like planets, you know, they might move very slowly, but they're there and they stay there in the sky. There are other things like supernovae, something called fast radio bursts, which again, these are a whole other field that if you want to look into it, there's some really interesting stuff going on there. But there are all sorts of scientific explanations as to why we might get a blip of a signal from somewhere in space and then not see it again, as with the WOW signal. And so yeah, they and again, the science is still ongoing as to where they come from and the physics behind them. So if you're interested in asking those kind of questions, astronomy may be a career for you. Let's see. Have you had any questions on Facebook at all? I've not been looking at them.
On that. We do have people viewing it on Facebook.
Hi, Facebook.
Maybe Emma, in a nutshell, maybe you can try to sort of explain a bit on this Nobel Prize in physics, what it was on, or just in a nutshell.
Yeah. So in general, so the Nobel Prize was split into, as the Nobel Prize often is nowadays, because actually one thing I will comment on is the fact that there is this, I guess, impression that science is done by lone geniuses working in a lab, kind of squirreling themselves away and working on theories. Like, maybe that's how science used to be done 100 years ago, but really now science is a hugely collaborative effort. And I think something that maybe going forward, the kind of a Nobel Prize, which is at maximum awarded to 3 individuals, actually it's quite hard to find individual credit for discoveries, because now science is very, very collaborative. But in terms of what the prize was awarded for, so half of it was awarded for, so that was to Penrose, so that was in developing the maths kind of behind black holes. So black holes are some of the kind of the most extreme environments that we know of in the universe, and require some quite detailed and complex maths in order to describe them. And if you know of Albert Einstein, probably one of the most famous physicists there is, so one of the things Einstein did was something called general relativity. So this is just kind of a set of maths and series of equations that describe the universe and the way that they interact. So the part of the Nobel Prize was for that, then kind of the mathematics behind black holes, and then the other half, so then was split into quarters, was related to observing black holes. So, and kind of I wish I put it in this talk, actually, because the reason why we know that there is a black hole at the center of our Milky Way galaxy is not because we can see it directly, but because of the effect that it has on the things around it. So if we look into the very center of our galaxy, what we can see is there are stars orbiting around something. and we can't see the something, but based on the motions of where the stars are going, we know what must be there in the middle, and what we know must be there is something that has a lot of matter, like weighs a lot, but we can't see it. And so so that half of the Nobel Prize was for kind of that, the observation. Was for the observation of black holes, and I think that's fairly typical for a Nobel, actually, in physics. If it is awarded for something observational or something experimental, usually the person who kind of was involved in the theory will be awarded that as well. And in fact, if Stephen Hawking had been alive this year, it's possible that he would have been included on the mathematical side of things, because that was something he was very much involved in too.
Okay, Emma, we're going to take this question from Facebook. Someone's asked, someone called Shanaz Awan has asked, can we come to the Jodrell Bank for view these stars and planetary bodies?
So usually Jodrell Bank Observatory is open. We have a wonderful discovery centre, which has got all kinds of exhibitions where you can learn a lot more about astronomy and the science that we do at Jodrell Bank. And in fact, it was, well, actually there's been a few things in recent years. So first of all, there's been a National Lottery grant fund that was given to the Discovery Centre. So actually at the moment they're developing a new kind of series of exhibitions there. I've not been myself in absolutely ages because I've not been into work. I've been working from home because of COVID. But yes, I think the Discovery Centre is now open again, and maybe not fully. Again, I've not been, so I don't know, I'm afraid. But yes, usually you can go and visit Jodrell Bank and kind of learn about all of the science that we do there. And sometimes there are stargazing sessions as well.
Another question from Facebook. Which astronomy society do you belong to? As I would love to join that one. You are so passionate and inspiring.
Oh, thank you. So I got started at so I'm from York, and I got started at the York Astronomical Society. So I still keep in contact with them. But again, with COVID, I've not really been leaving Manchester much. But I've done a few things with the Manchester Astronomical Society as well. So they're a good bunch. So really, it's just okay. I would say, honestly, if you enjoyed listening to me talk tonight, and I'm really very flattered by that, thank you. Honestly, any astronomical society, there will be someone who can talk your ear off about astronomy. So I think at the moment, obviously, it's difficult because astronomy societies are not meeting in person. But honestly, any local astronomical society, find out where your local one is near you. I guarantee there will be someone who is happy to talk to you about astronomy as much as I am.
Okay. Do we any in the chat box, or have you gone through them all? Or
I have. Oh, I may have missed a couple, but I think I've answered the ones on Zoom.
Okay, thank you very much. I think we should wrap up now with this time. So once again, thank you very much, Emma, for an excellent presentation. Yeah, and I'm sure there's a lot of interest, a lot of questions, and we've had people joining from Facebook as well. And just like to thank everyone for joining us. And I'm sure everyone, a lot of the youngsters who've joined in have found this very interesting. And this is one of the aims of Young Professional Society, that we've been set up to actually help youth, the young people, with personal and professional development. So we focus on 3 pillars, innovation, leadership, and communication, trying to help youngsters build their soft skills. And we've been collaborating with the STEM Matters from the US as well, and we've been live streaming on Facebook on STEM Matters page as well. So we've got people joining us from Dallas as well as we speak. So it's great to have you, Emma, and people who would like to know a bit more about YPS, Young Professional Society. We are on Facebook as well, and we're conducting these webinars. We're trying to bring in people from different backgrounds, professionals, and who advise and give information to the youngsters and inspire them and help them. So once again, thank you very much, everyone, and thank you, Emma, and have a nice evening, and keep safe. Thank you for joining.
Thank you. Bye-bye.